Today we're talking about manufacturing measurements. So this is very much kind of a concept that's important throughout your manufacturing career, whether you're on the shop floor or you're a maintenance technician, or you are all the way up at a plant manager, or maybe even you're running an entire business. Measurement, if you can't measure, you can't improve, is the general rule of thumb, which isn't entirely true, but it's often true. One way we measure is we record data, and then we look at how that data appears to be running. Is it doing well? Is it not doing well? So one way that we can measure whether data is doing well is we apply it to standards. And I'm not going to get into the details of the math, but we're going to talk about in a typical manufacturing operation, how you would collect data. We're going to talk about how the results might be measured. And we're going to give you a standard, a classic charting technique, which many manufacturing facilities use right now. And then we're going to finish off this quick topic with what is Sigma. So when I first started working, and I worked for a guy who looked very much like this guy. I found this guy on the internet. Don't know him personally, but what I was doing in my very first job right out of college, in fact, I think it was between my junior and senior year, I worked in a machine shop, and basically he had me taking chunks of steel and cutting them off into little billets about 6 3/4 inches long. And he had some guy set it up for me. And all I did was just feed these billets of steel into this machine and bring this big bandsaw down and chop off these steel billets. And at the time, I was completely clueless. I sucked at it. In fact, I sucked so bad that when the process started drifting off, I didn't do anything about it because I wasn't told to do anything about it. All I was doing was chopping off these pieces and not really measuring them very carefully. In the end, we had to get more raw material because I screwed up so bad. And so I didn't do so well. I didn't keep that job very long. The problem is when you are doing a manufacturing operation and you've got a clueless operator, or you've got a machine that's starting to screw up, then you start to miss the target. And every time you have a target, it usually has a lower limit. In other words, that billet has to be a minimum length, and it has an upper limit, a maximum length. In my case, the minimum length was critical because it had to be slightly bigger than the finished product. Whereas the maximum length, if I use too much, it means I would use too much of my raw material too quickly. And that would be a problem as well, because that means I run out of raw material before I finished producing all the good. So the first step in my operations was measuring. And in this case, I'm showing the use of very inexpensive plastic caliper to do measurement. So you take a measurement and then you record that measurement. And the idea is you may not take a measurement of every single piece. You might take every 5th piece. And then over time, you record what that measurement is. This is what's called an X bar R chart, which is kind of critical. Down, every time you had a recorded measurement, you'd make a little dot. Each one of these little dots is a recorded measurement. So let me use my laser pointer. So here's a recorded dot, and here's a recorded dot, and here's a recorded. So every time I made a measurement, and the measurements range from 0 to 4, you know, the precise measurement that I was looking for in the case of this chart was about 1.8, I think. And so you always put a line down the middle of your chart indicating that that is your target. Below your target, you've got your minimum, right? That's the lowest level. If you drop below that, I mean, you can't use that part anymore. You have to throw it away. And then on the other side, you have your upper level. Also might mean you have to throw the product away or have to run another step on it to chop it shorter. So you've got that range in between. That's a good part. And your X bar R just basically shows you tracking the measurements as they vary from period of time to period of time, and how they're doing. And the reason why we create an X bar R chart is so that if we start to see our, even if the product is good, it starts to get smaller and smaller and smaller, like my cutoffs were getting. That's because I didn't notice there was some buildup of chips between my stop and the part I was cutting off. Then I would stop the process and go, why are my products trending down? Even if they're still within a valid range, they're trending down smaller and smaller. With a chart like this, I can see that trend and stop the process, clean out my chips, and restart it. So this is a classic measurement system for manufacturing. It's called an X bar R chart. So that's what you use in manufacturing. You're going to see something like this, either an automated tool, which collects data automatically, or a manual tool, which is still true in many plants today, that does this exact thing. All it does is show your measurements, whether it's a physical measurement or some sort of analysis, and then compare it over a period of time to see how it's doing. We take those measurements, and now over, say, a full day or a full week, we can totalize them so that in the range of good parts, right, say 50 centimeters at the bottom is your good part range. You've got 20 in the range of 50 centimeters, say between 50 and 51 centimeters or maybe millimeters long, and 25 in that 50 to 51, 26 in that 51 to 52. You totalize them over a period of time. And what you see is those totals create this funny little curve, so that once in a blue moon, you get things out at the end of the curve. That means something screwed up. But for the most part, with a normal process that has random occasional problems, your good parts are, you have a very nice high curve right in the center there. This totalizing gives me a curve. It's a typical curve. So that curve is considered the standard deviation measurement. So within plus or minus one standard deviation, and a standard deviation is it's a mathematical calculation. I'm not going to get into it now, but you can either look it up on Google, or if you've done any statistics classes, you know what that mathematical calculation is. But in a normal curve of distribution of parts, one standard deviation means that 68% of the parts fall within one standard deviation, plus or minus one standard deviation. Whereas 95 of the parts fall within plus or minus two standard deviations. 97% of the parts fall between three standard deviations, plus or minus three standard deviations. And 99.9997, I have to look up the number exactly, an extremely small percentage of parts fall outside of six standard deviations, plus or minus six standard deviations. And that totalizing of defects is how you get to a standard deviation.